All right. Do you guys remember playing the Starburst game last week?
Yeah.
So, what did we do to play the game? Somebody describe the game to me. Yep, 4 red, 2 yellow Starburst in the bag. Absolutely. Okay, so a couple things. We returned the first Starburst into the bag. So we played this game, we would say, with replacement. We played the game with replacement because you're returning that Starburst into the bag. Friday, we talked about independent events when we talked about the Evil Eyebrow and Taco Tongue. What does it mean for 2 events to be independent? Yes.
The probability of this one is not the second.
Yes, the probability of one event, whether it does or doesn't happen, does not affect the probability of the second event. Are these 2 events, the first Starburst being red and the second Starburst being red, independent? Yes. Why? We had this replacement. So what's the probability of getting red on the first draw? 4 out of 6. We put the Starburst back. What's the probability you get red on the second draw? 4 out of 6. Doesn't matter what you got the first time. The probability stayed the same. Knowing whether or not the first is red does not change the probability that the second one is red. For independent events, to find the probability of the intersection, the AND, we multiply the probability of event A times the probability of event B. If I let event A be the first Starburst is red, and I let event B be the second Starburst is red, what is the probability that the first one's red and the second one's red? (16 out of 36). 4 over 6 times 4 over 6 gives us 16 over 36. That wasn't the only way to win the game, though, was it? How else could you win the game? 2 yellows. What's the probability that the first is yellow and the second is yellow? 4 out of 36. You do 2 out of 6 times 2 out of 6. We get 4 out of 36. Those are the 2 possible ways of winning the game, right? Is there any way to win the game by doing both of these at the same time? No. I can't win by getting 2 reds and at the same time, in that same moment, win by getting 2 yellows. So what's the probability of winning the game overall? 20 out of 36. We do 16 out of 36 plus 4 out of 36. I can just add them together because there's nothing in the intersection. These are mutually exclusive events. To get a probability of about 0.556. Roughly 56%. All right, now that we've had that refresher, we're going to play the Starburst game again, but with a little change. I want to explain the changes to you. You're going to need to find a partner. If your partner from last time is here, partner up with the same person. You guys are going to come and get a bag of Starburst. Those are up here at the front underneath the board in that box. But again, let me explain the rules this time around. Your group is going to play 10 times total. Just like last time, winning means you get matching colors. So you're going to get your bag. You're going to shake it up. Person A will reach into the bag and grab a Starburst. But they will not replace the first Starburst before getting the second one. So you reach into the bag, you grab your Starburst, you set it down on the desk. Person B shakes up the bag again. Person A reaches in and gets their second starburst. If they match, you win. If they don't match, you lose. Then everything goes back in the bag. That's the end of one game. And then person B gets their turn. You're going to play 10 games total, so 5 per person. We have 22 people in the room today, so everybody should be able to find a partner. After you've partnered up, I'll ask for who does not have a partner, and I will match you guys up. So everybody should get a partner. And then you can come up and grab one of these bags and start playing your rounds. So go ahead and find your partners now. Once you have found a partner, you can come and get a bag. Keep track of how many wins there are in 10 games. I'm going to ask at the end how many wins there are.
That is my bad. Wait, let me take it back out.
Okay.
The chance is gonna still be the same. That's not the I don't know if that's watch this go. No. There's no way. No. Watch it go. Watch it. You have one. I pulled yellow first. Every single time. I'm pulling yellow, red, yellow, red, yellow, red. I cannot.
No. 10 games total. Keep track of how many wins. You guys done?
Yeah.
How many wins?
7.
7. Nice. Are you guys done? How many wins?
7.
7. Oh my goodness. Thank you. How many wins? 5.
My knuckles are bruised.
You? Are you guys done? How many wins? 6. you. Did you guys finish up? How many wins? Two. No worries. Last round, or last period I had somebody just get one. So, had a couple of groups get twos. You guys done?
Yes.
All right. 3 wins. Awesome. 5 wins. Fantastic. Steal that from you. You guys done? How many wins? 6. Big numbers in here today. 1, 2, 3, 4, 5, 6, 7, 8.
Yeah, we won 8 times.
10, 11. Okay, perfect. All right, you guys might want to start adding these numbers up. We've got 3 more numbers to include on the list.
You only have 3 wins. I have 2.
You got 8 total? Wow. All right.
We're winning.
Thank you.
We are winning.
I'll get one more guy.
How many wins? 2. No worries. Thank you.
Wait, maybe that was all of them.
Did you not write it down?
You suck.
All right. How many wins?
5.
5 wins. Okay. All right, let's add these up. We're going to find the estimated probability of winning this game. So add these up for me. 21. 35, 40. What do you guys get when you add them up? 56? 56? Okay, that's what I got too. But I did it in my head, so I needed other people to confirm. 56 out of how many games were played total? 110. So let's calculate the probability, the estimated probability of winning this game. What is 56 divided by 110? How much? 0.509. Or that would be about 50.9%. What was the probability of winning when we were putting them back? Yeah, like 55, 56%. So what happened when we would take the starburst out and leave it out for the second draw? Probability of winning went down, or at least it appears to have gone down, right? So last week when we played this game, when we wanted to find the theoretical probability, the true probability of winning the game, we made a sample space of all the possible outcomes, right? We're going to do something slightly different today. We're going to do something called a tree diagram. Have you guys ever seen a tree diagram before? Got a couple people that have seen it. A tree diagram is how you handle probabilities when we have 2 events and the probability for the second event changes based on what happened in the first event. Is the probability of getting the first one red and the second one red still independent? No. What's the probability that the first starburst is red? 4 out of 6. So I can go ahead and put that here. For my starburst game, the probability that the first one is red is 4 out of 6. What's the probability that the second one's red? 3 out of 5. Now there's only 5 starburst in the bag and only 3 of them are red. So how do you think I would find the probability that the first one is red and the second one is red? What did we do with those probabilities before when they were independent? We multiplied them. Let's multiply these. These events aren't independent, but let's go ahead and multiply anyway. We're going to multiply 4 over 6 times 3 over 5. And that gives us what? 12 over 30. That 12 over 30 right there is the probability that the first one was red. That's that 4 out of 6. Times the probability, ooh, I should write first red instead of just red. Probability that first is red times the probability that the second one is red, given that the first one was red. It's not just a basic multiplication anymore, but I'm still multiplying my probabilities together. I can't just take the probability of event A times the probability of event B. If event B is my second starburst is red, it changes based on what I grabbed the first time, right? Like, what's the probability that the first starburst was yellow? 2 out of 6. And if the first one really was yellow, what's the probability that the second one was red? 4 out of 5. So the probability that the second starburst is red changes based on what happened the first time. I'm still multiplying, but I can't just multiply the probability of event A to the probability of event B, because the probability of event B depends on the first event. And that's why we write it this way. We multiplied the probability that the first was red, 4 out of 6, by the probability that the second was red, given that the first was red. All right, let's see if we can find this probability here. What is the probability that the first one was yellow, but the second one was red? What operation are we doing? 8 over 30, yes. We're going to multiply along those branches. We multiply this path to this path, and that's how we get this. What's the probability that you grabbed a red the first time, but a yellow the second time? Yeah, yellow the second time, if my first one was red, would be 2 out of 5. I don't know what happened to my 2. It disappeared. So what's the probability that the first one was red and the second one was yellow? 8 out of 30. What's the probability that the second one would be yellow if the first one was yellow? If the first one was yellow, 1 out of 5. If the first one was yellow, you got the yellow and then you set it on your desk. It's not in the bag anymore, so now there's only 1 yellow in the bag. So what's the probability that you won the game by getting 2 yellows? 2 out of 30. I want you guys to look at these orange fractions. Oops, some of my numbers disappeared and I don't know why. 4 out of 6, 2 out of 5, there we go. I have 8 out of 30, 8 out of 30, 2 out of 30. I want you to add all of those up for me. Where's 12 over 30 plus 8 over 30 plus 8 over 30 plus 2 over 30? 30 over 30. Which simplifies to what? Simplifies to 1. When you add up all of these ending probabilities, I like to think of them like leaves. They're on the ends of the branches. When you add up all of those ending probabilities, it should always add up to 100%. Now here's something kind of interesting too that you can use to check yourself along the way. Do you see how these two came off of this main branch here? What happens if you add 12 out of 30 to 8 out of 30? You get 20 out of 30, right? 20 out of 30 is what is a decimal? 0.6 repeating, or 0.67, right? So is 4 out of 6. The ending leaves along this branch should always come back and add up to this much back here. What's 8 out of 30 plus 2 out of 30? 10 out of 30. What's 10 out of 30 as a decimal? 0.3 repeating. What's 2 out of 6? 0.3 repeating. These leaves here should add up to this main branch back here. And all of those little ending pieces should always add up to 1. Beautiful. Let's see if we can use this tree diagram now to answer a couple of questions. I want the theoretical probability of winning. Right here we have our experimental probability of winning. We got 50.9%. Which of these outcomes would result in a win? First and second red, this one. First and second yellow, this one right here. So what's the probability of winning? 14 out of 30. Find that as a decimal for me. .46 repeating. We did 12 out of 30 plus 2 out of 30 to get 14 out of 30, or 0.46 repeating. Our experimental probability was higher than that, wasn't it? What do you think we could have done to get closer to that number? Play the game more. What are we using if we play the game more and more and more and more and more? Law of large numbers. The more trials we add, the closer and closer we get to the theoretical probability. What is the probability that the first candy was red, given that the person won the game? Got some conditional probability thrown in here. What is the probability that the first candy was red, given that the person won the game? How much? 12 out of 14 is absolutely correct. So 0.857, about 86% chance. If you won the game, you probably did it by getting 2 reds. Let's talk about how to get that now. My given that should look like this. The probability that the first is red, given that the person won the game. So I've got this line right here for my given that. Does anybody remember from Friday what should go in the numerator when we have a conditional probability? In the numerator, I want the intersection of these two things. So my numerator, I want the probability of first and win, both of them together. What should go in the denominator? The probability of win, yes. My condition goes on the bottom. Here's my condition. My intersection up on top. Well, according to our tree diagram, what was the probability of first red and win? 12 out of 30. What was the probability of just win? 14 out of 30. That was question number 5. I've got two fractions inside another fraction. That's gross. But what do you notice about these two denominators? They're exactly the same. If I have two fractions inside of a larger fraction, one on top, one on bottom, and both of those fractions have the same denominator, they will cancel each other out. All right. Let's flip this over. There was a lot going on here today. Let's see what we picked up. All right, up at the top. Oops. Get rid of this. My general multiplication rule. If I want to find the probability of the intersection A and B, I multiply the probability of A times the probability of B given that A. This is what allows me to multiply along those branches. If A and B are independent, then the probability of B given A is just exactly the same as the probability of B. So that simplifies my equation a little bit. My tree diagrams, you can make very complicated tree diagrams. We are only going to look at situations where there's two choices for the first event, two choices for the second event. So my first branching here, we have the probability of A and the probability of not A, or A complement. And then my second branching coming off of both of these, probability of B given A, probability of C given A. Probability of B given A complement, probability of C given A complement. That will give me the probability of A and B, A and C, A complement and B, A complement and C. And it should always add up to 1. And then this last little note at the bottom, I have mentioned this before. I will mention it again. I'm sure I will mention it lots and lots and lots of times because this one's really important. If I want to know the probability that something happened at least one time, I would do 1 minus the probability that it didn't happen at all. Rather than add up all the ways that it could happen, I will do 1 minus the probability that it didn't happen. So far, so good? All right. I'm going to give you guys about 2.5, 3 minutes. I want you to do just number 1. Just create the tree diagram on the check your understanding, because all of the other questions rely on this. So take about 2.5, 3 minutes to create the tree diagram based on this situation. If somebody walks into a clinic, they want to take a rapid flu test. What are the 2 possible things that could be going on with that person? They have the flu or they don't have the flu. What's the probability that the person comes in sick and has the flu? 22% or 0.22. I'm going to always write this down on my tree using decimals, not percent signs, because I know I'm going to be multiplying these branches together. So if it's a 0.22 probability that the patient has the flu, what's the probability that they don't have the flu? 0.78. Okay, so they walk in to take this rapid flu test. They either do have the flu or they don't when they come in. We don't know which it is, but they got one of those two things going on. They take the rapid flu test, and what are the possible outcomes of the rapid flu test? Negative or positive? What did it say up above? If the patient really does have the flu, what's the chance this test comes back with a negative result? 3.7% or 0.037. What's the other possibility? That it's positive. What's the probability that they really did have the flu and it came back positive? Yes, 0.963. How do we get that number? 1 minus this, because these branches should always add up to 100%, because it's either got to be positive or it's negative. So how do I find the probability that the patient really does have the flu and they have a positive test result? Multiply. Multiplying those two together, you should get 0.21186. What do we get when we multiply a patient with the flu times the probability that they get a false negative? What's the probability that they have the flu and they tested negative? Yeah, 0.00814. Please don't get into the habit of just rounding to 2 decimal places. You see why that would be a problem here. That is not a probability of 0. It is very small, but it's not a probability of 0. That's almost 1%. And what should these two numbers add up to? 0.22 back here. If the patient doesn't have the flu, what are the possible outcomes of this test? Positive or negative again? If the patient doesn't have the flu, what's the probability that that test came back as a positive? 0.026, 2.6%. So if they don't have the flu, what's the probability that the test comes back negative? 0.974. So the probability that they don't have the flu and it came back as a positive test? .02028, so about a 2% chance that they tested a false positive. And the probability that they don't have the flu and the test came back as a negative. Yes, 0.75972. These last two numbers, just these two, should add up to what? 0.78. And all 4 of these ending numbers should all add up to what? Should all add up to 1. All right. I'm going to give you guys about 3 minutes to answer the remaining 3 questions. Some of it relies on the tree diagram. Some of it relies on critical thinking or what we did last week. So some of it is directly related and some of it is tangentially related. What's the probability of a positive test result? Yep, 0.23214 if you take it all the way out and include all the decimal values. That's the probability of getting a positive given that they have the flu, plus the probability that they have a positive given that they don't have the flu. These came right off the tree diagram. You add those together to find the probability of a positive. So I want to show you on the tree exactly where I got these numbers from. This one right here, because that is positive, and this one right here, because it is also positive. So those are the two numbers that we're adding together. If we select 4 patients at random, what's the probability that at least one of them gets a positive result? How should I approach this for an at least one? 1 minus the probability of none. Well, none would mean what kind of a test result? A negative test result. What's the probability that just any one person gets a negative? There's my probability of a positive. So what's the probability of a negative? Yep, 0.767 something something. Yep. So that's for one person. What would the probability be for a second person? Times it. What about for a third person? Times it again. For a fourth person? Times it again. So, probability of 4 negatives would be the probability of a negative to the 4th power, so 0.76786 to the 4th power. And we do 1 minus that to get 0.65236. This last one is a given that. What do we know about this patient? They had a positive result. So that's what's going to go after the bar. Given that bar, they have a positive. What is it that we wonder about this person? Do they actually have the flu? So my probability notation would look like this. So as I'm trying to calculate this, I know I need a fraction, because given that always means a fraction. What would go up in the numerator? Both intersecting. So what's the probability of flu and positive? Should come right off your tree. What's the probability of flu and positive? 0.211 something something. What's the what goes on the bottom? Positive. What's the probability of a positive? 0.23214. That's what we found up in number 2. So now I divide those two, and I get what? Yes, 0.91264. So if somebody comes back with a positive test result, it's more than a 90% chance that they really do have the flu. Because sometimes we get negative results. Sometimes. Don't forget, homework is due tomorrow. Please come in with that ready to go. Test is on Friday.